A separately derived system for a generator has several advantages. Firstly, there's no need for a grounding electrode. Since the system is electrically isolated from the main electrical system, it does not require a dedicated grounding electrode. Secondly, a separately derived system reduces ground fault risk. The separate grounding system minimizes the risk of ground faults affecting the main electrical system. Thirdly, it offers improved fault protection. The separately derived system provides additional fault protection by isolating the generator from the main electrical panel. Fourthly, maintenance is easier. Troubleshooting and maintenance can be simpler with a separately derived system, as it is independent from the main electrical system. Now let's consider the advantages of a non-separately derived system. Firstly, the installation cost is lower. This system does not require a separate grounding system or bunting, resulting in reduced installation costs. Secondly, less space is required. Non-separately derived systems do not require additional space for a separate grounding electrode. Thirdly, the wiring is simplified. The wiring is simpler and more straightforward compared to a separately derived system. Fourthly, there is compatibility with existing systems. This system is compatible with existing electrical systems, making it easier to integrate the generator. When deciding between a separately derived system and a non-separately derived system, consider several factors. If the generator is trailer-mounted, it is often easier to install it as a separately derived system, as it can be easily disconnected and moved. If there is a large electrical system with multiple panels and complex grounding, a separately derived system may provide additional safety and fault protection. If cost and simplicity are the main concerns, a non-separately derived system may be more suitable. A separately derived system may provide additional benefits for a trailer-mounted 36-grid three-phase generator, such as improved fault protection and easier maintenance. Ultimately, the best decision depends on specific circumstances and preferences. A separately derived system, or SDS, is an electrical power system in which a generator supplies power that is not directly connected to the utility power source. This electrical isolation creates its own ground reference, different from the existing electrical system. Key components include the generator itself, a transfer switch to select between utility and generator power, and the grounding system specifically for the generator. The grounding system typically involves a grounding electrode conductor connected to a grounding electrode, such as a ground rod or a metallic water pipe. National Electrical Code, or NEC, Article 250 covers the grounding requirements for separately derived systems. A non-separately derived system, also known as a non-SDS, involves connecting the generator to the existing electrical system without electrical isolation. This means the generator shares the same grounding system as the utility power. Key components here include the generator, a transfer switch, and the existing building's grounding system. The generator is connected to the main electrical panel and its neutral conductor is bonded to the panel's grounding bus. NEC Article 702 covers optional standby systems, which include non-separately derived generator systems. Grounding requirements for non-SDS systems are covered in NEC Article 250 as well. When selecting between these systems, consider grounding requirements. In a separately derived system, a grounding electrode system must be established at the generator location. This ensures a solid ground reference for the generator's power output. In a non-separately derived system, the generator uses the existing building's grounding system. This simplifies installation but relies on the existing grounding being adequate. The presence of ground faults also becomes a consideration. A separately derived system minimizes the impact of ground faults on the main electrical system. A ground fault on the generator side will not directly affect the building's electrical system. In a non-separately derived system, a ground fault on the generator can potentially affect the entire electrical system, so overcurrent protection must be carefully coordinated. Separately derived systems provide isolation. Separately derived systems electrically isolate the generator from the utility power. This isolation can improve power quality and reduce the risk of electrical noise or surges affecting sensitive equipment. Non-separately derived systems do not provide this isolation. The generator is directly connected to the electrical system, so any disturbances on the generator side can propagate to the building's electrical system. Next, think about installation costs. Separately derived systems generally have higher installation costs due to the need for separate grounding electrode system and additional wiring. Non-separately derived systems typically have lower installation costs since they utilize the existing grounding system. When it comes to maintenance and troubleshooting, separately derived systems can be easier to troubleshoot since the generator's electrical system is isolated from the building's electrical system. Problems can be more easily traced. Non-separately derived systems can be more complex to troubleshoot since the generator and building electrical systems are interconnected. Faults can be harder to isolate. Look at code compliance. Separately derived systems must comply with NEC Article 250 for grounding requirements. This includes proper sizing of grounding electrode conductors and the installation of grounding electrodes. Non-separately derived systems must also comply with NEC Article 250, but the focus is on ensuring the generator is properly bonded to the existing grounding system. Transfer switches play a vital role. For both systems, a transfer switch is used to switch between utility power and generator power. The transfer switch must be properly rated for the generator's output and must be installed according to NEC requirements. Consider the size of the generator. For larger generators, a separately derived system may be preferred to ensure proper grounding and fault protection. For smaller generators, a non-separately derived system may be adequate. Consider the application as well. In critical applications where power quality and reliability are paramount, a separately derived system may be the better choice. In less critical applications, a non-separately derived system may be sufficient. Now, let's think about the specific components of a separately derived system in more detail. The grounding electrode conductor, or GEC, connects the generator's neutral terminal to the grounding electrode. The size of the GEC is determined by NEC Table 250.66 based on the size of the generator's conductors. The grounding electrode should be a ground rod, a metallic water pipe, or a concrete encased electrode, as specified in NEC Article 250. The bonding jumper connects the generator frame to the neutral terminal. This ensures that the generator frame is at the same potential as the neutral conductor. The size of the bonding jumper is determined by NEC Table 250.102. In a non-separately derived system, the generator's neutral conductor is connected to the building's main grounding bus in the main electrical panel. The connection must be properly sized to handle the generator's fault current. The generator frame must also be bonded to the building's grounding system. This ensures that the generator frame is at the same potential as the building's ground. Overcurrent protection is essential in both systems. The generator must be protected by overcurrent devices, such as circuit breakers or fuses to prevent damage from overloads or short circuits. The overcurrent devices must be properly sized to protect the generator's conductors and equipment. Coordination of overcurrent devices is crucial to ensure that the overcurrent device is closest to the fault trip first, minimizing the extent of the outage. In a separately derived system, the overcurrent devices must be coordinated with the generator's impedance to ensure proper fault protection. In a non-separately derived system, the overcurrent devices must be coordinated with the building's electrical system to ensure proper fault protection. Now, let's talk about some common misconceptions about separately derived systems. One common misconception is that separately derived systems are always required for generators. This is not true. The NEC allows for both separately derived and non-separately derived systems, depending on the specific application and the size of the generator. Another misconception is that separately derived systems are always safer than non-separately derived systems. While separately derived systems do offer some advantages in terms of fault protection, both types of systems can be safe if properly designed and installed. To ensure the safety and reliability of either type of system, it is important to follow all applicable codes and standards, including the NEC. It is also important to have the system inspected by a qualified electrical inspector to ensure that it is properly installed and grounded. Consider the load characteristics. Separately derived systems are beneficial when supplying sensitive electronic equipment due to their ability to isolate the load from the utility power's noise and fluctuations. Non-separately derived systems might be sufficient for simpler loads like lighting or heating. Think about future expansion. If there are plans to expand the electrical system in the future, a separately derived system can provide more flexibility and scalability. A non-separately derived system might be more limiting in terms of future expansion. A separately derived system isolates the generator's power from the utility grid, which can prevent backfeed and protect utility workers. A non-separately derived system requires careful coordination with the utility to prevent backfeed. Emergency power systems are required to meet specific requirements outlined in NEC Article 700. These systems are designed to provide power to essential loads during a power outage, such as emergency lighting, fire pumps, and life safety equipment. Standby power systems, covered in NEC Article 701, provide power to non-essential loads during a power outage, such as HVAC systems, refrigerators, and other appliances. Optional standby systems, covered in NEC Article 702, provide power to loads that are not critical for safety or operation, such as comfort lighting, entertainment systems, and other non-essential equipment. The NEC provides specific requirements for the installation and wiring of generators used in these systems, including requirements for transfer switches, overcurrent protection, and grounding. In healthcare facilities, generators are often used to provide emergency power to critical loads, such as life support equipment, operating rooms, and intensive care units. The NEC has specific requirements for the installation and wiring of generators in healthcare facilities, including requirements for redundancy, testing, and maintenance. In industrial facilities, generators are often used to provide standby power to essential loads, such as production equipment, control systems, and safety systems. The NEC has specific requirements for the installation and wiring of generators in industrial facilities, including requirements for coordination with other electrical equipment and systems. When selecting a generator for a specific application, it is important to consider the power requirements of the loads that will be served by the generator. The generator must be sized to provide sufficient power to meet the demand of all connected loads, with some margin for future expansion. It is also important to consider the voltage and frequency requirements of the loads. The generator must provide power at the correct voltage and frequency to ensure proper operation of the connected loads. Another factor to consider when selecting a generator is the type of fuel that will be used to power the generator. Generators can be powered by gasoline, diesel, natural gas, propane, or other fuels. The choice of fuel will depend on factors such as availability, cost, and environmental considerations. Regular maintenance is crucial to ensure the reliable operation of a generator. Maintenance tasks include checking the oil level, changing the oil and filters, inspecting the cooling system, and testing the generator under load. It is also important to keep the generator clean and free of debris. A qualified electrician should perform maintenance on generators according to the manufacturer's recommendations. Understanding surge protection for generator systems is also crucial. Generators, like any electrical system, are susceptible to voltage surges caused by lightning strikes, utility switching, or internal equipment faults. These surges can damage the generator itself and any connected equipment. Surge protective devices, or SPDs, are designed to limit these transient voltages and divert surge current away from sensitive equipment. They are a critical component in protecting generator systems. NEC Article 230.67 outlines the requirements for surge protection in dwelling units, and Article 700.8 addresses surge protection for emergency systems. While these articles don't explicitly cover all generator installations, they provide a good guideline for implementing surge protection. There are different types of SPD available for generator systems. Type 1 SPD are installed at the service entrance and are designed to handle the highest surge currents. Type 2 SPD are installed at distribution panels and protect branch circuits. Type 3 SPD are installed at the point of use and protect individual pieces of equipment. For a generator system, a Type 1 or Type 2 SPD should be installed at the generator output to protect the generator and downstream equipment. Type 3 SPD can be used to protect sensitive equipment connected to the generator. When selecting an SPD, several factors should be considered. Surge current capacity is the maximum surge current that the SPD can handle without failure. The SPD should have a surge current capacity that is appropriate for the expected surge environment. Voltage protection rating, or VPR, is the maximum voltage that the SPD will allow to pass through to the protected equipment. The lower the VPR, the better the protection. The SPD should have a VPR that is compatible with the voltage requirements of the protected equipment. The SPD should be listed by recognized testing laboratories such as Underwriters Laboratories or AL to ensure that it meets safety and performance standards. The location where the SPD is installed is also important. The SPD should be installed as close as possible to the equipment being protected. This will minimize the length of the conductors between the SPD and the equipment, which will reduce the voltage drop caused by the surge current. The SPD should be properly grounded to ensure that the surge current is effectively diverted away from the protected equipment. The grounding conductor should be as short and straight as possible. Proper installation of SPD is crucial for effective surge protection. The SPD should be installed by a qualified electrician in accordance with the manufacturer's instructions and all applicable codes and standards. The SPD should be inspected regularly to ensure that it is functioning properly. If the SPD has been subjected to a large surge, it should be replaced. Surge protection is an important consideration for generator systems. By installing SPD, you can protect the generator and connected equipment from damage caused by voltage surges. Remember to select the appropriate type of SPD for the application, consider the surge current capacity and VPR, and ensure that the SPD is properly installed and grounded. Regular inspections and maintenance are also important to ensure that the SPD are functioning properly. This helps you maintain the reliability of the generator system and protect valuable electrical equipment.